A small sphere of radius 2 centimeters falls from rest in a viscous liquid. Heat is produced due to viscous force. The rate of production of the heat when the sphere attains its terminal velocity is proportional to. Four options are here. Let us find the right one. Here you have a tall jar filled with high viscous fluid or liquid of density sigma. Let us consider a solid sphere of density rho that falls through this liquid at constant terminal velocity Vt. So the acceleration is 0, the net force during its journey is 0. Now we consider this solid sphere somewhere at the point, a middle point during its journey. Let us find how many forces are available here. The downward weight Fg, the upward buoyant force Fb, and the upward viscous force Fv. The viscous force always opposite to the direction of its motion. Good. At Vt, no acceleration, no net force available on the solid sphere. So we can say that net downward force equals net upward forces. Therefore, Fg equals Fb plus Fv. What is Fg? It is gravitational force. What is Fb? It is buoyant force. And what is Fv? It is viscous force. So, Fg can be written as mg, that's equal to mass means volume into density. So, we get 4 by 3 pi r cube rho g. R is the radius of the solid sphere, rho is the density of the solid sphere, g is the acceleration due to gravity. Then Fb equals the weight of the liquid displaced by the solid sphere, that's equal to 4 by 3 pi r cube sigma g. Here sigma is the density of the liquid. Then buoyant force Fb equals 6 pi eta r Vt. Eta is the coefficient of viscosity of the liquid, Vt is the terminal velocity. This is from Stokes' law. So let us write here Fg minus Fb equals Fv. Fg minus Fb equals Fv. Let us substitute the value of Fb and let us substitute the value of Fb and let us substitute the value of the viscous force 6 pi eta rvt. Now, on the left hand side, let us take the common term. They are 4 by 3 pi r cube. Within bracket, we have rho minus sigma multiply g equals 6 pi eta rvt. From this formula, let us find the terminal velocity Vt equals 2 upon 9 multiply r square rho minus sigma multiply g divided by eta. The power dissipated due to the viscous force is given by power P equals the viscous force multiply the terminal velocity. Let us substitute the viscous force 6 pi eta r Vt multiply Vt. So we get P equals 6 pi eta r Vt square. Let us substitute the Vt here in the formula. We get P equals 6 pi eta r multiply 2 by 9 multiply r square rho minus sigma within bracket multiply g divided by eta to the power 2. Good. So, squaring the terms within the bracket, we get, and let us remove the constant quantity like 6 pi, let us remove it, and 2 by 9, let us remove it. The 1 eta cancels with eta square in the denominator, we have only eta. Here you have r and r square, we get r power 5. Then we have r minus sigma to the power square and g square. And remember, this is the form, final form. The power dissipated due to viscous force is proportional to r power 5 multiply rho minus sigma square g square divided by eta. Here, in our problem, the rho, g, sigma, eta are all constant. So, we have only one variable term in our problem, that is the radius. So, power is proportional to r power 5. The r is given in our problem as 2. So, we have P proportional to 2 power 5. The option D is correct.